you. Hi, everyone. Welcome to CS32 Interview Prep, the third session. We're going to be talking about linked lists today. To give a short reintroduction for those of you who are new or haven't been caught up, my name is Bill, and my assistants today are going to be Anna and Sartek, if they'll introduce
Was
themselves.
was that a pause for us? I'm Anna, third year CS. I think you've known me. I also helped lead the first session.
And I'm Sarthak, second year CS major.
Yep, and I'm Bill. I'm a third year CS major, and you might remember me from coding review crash course from the fall quarter. All right, so before we get started, please go ahead and fill out, or not fill out, but if you want to, enter the ACM portal code, cool nodes. You'll get a lot of points from entering this code. And I believe each quarter, the people with the highest points and like the second highest points get a prize. So look forward to that. And if you guys, I guess I'll stay here for 10 more seconds. All right. And here is the slides for this week's session. So you can either use the QR code using your phone if you don't want to bother filling out the actual link, or you can use the TinyURL. And I'll stay here for around 10 more seconds. We'll also be probably pasting the link in the chat. My assistants will probably go ahead and do that. But without further ado, before we get started, I'd like to just poll just to see everyone's comfort level with linked lists and sort of how much they've done or how comfortable they feel using them in interviews. And so we're going to launch a poll, and we're going to try to guide our session and our lessons around your comfort level. Okay, great. It looks like everyone is pretty comfortable with them. So I'm going to try to guide my lesson towards more tips and tricks, and towards people who are more comfortable with them and are ready to use them in a more advanced form or in more advanced forms. Okay, cool. Let's get started then. So here is a quick meme. So if you guys didn't know, HTML actually has something called linked lists, although they're not the linked lists that we're going to talk about today. They're not the linked lists that are most commonly referenced in CS32 or in coding interviews, but they do have something else that's completely different, but it's called the same thing. So make sure you know what you're talking about. Okay, so quick recap to jog your memory, because I'm sure you've been taught in CS32 about linked lists. And in case you were like, okay, I know about linked lists, but I don't exactly remember what it is, here's a quick recap. So linked lists are a data structure, just like arrays are a data structure, sets are a data structure, hash maps are a data structure. And it's basically what it is a list of objects called nodes. And the node has two actual parts, the actual data and the pointer to the next node, as you can see in this cool diagram here. Usually we start at the head of the list, and usually you're given the head of the list at the part of a problem when you do a linked list problem in an interview. And there's often a couple of different types of linked lists. So you can have like singular linked lists, doubly linked lists, and circularly linked lists. I'll talk about a lot more about this later, but that's just a quick recap to jog your memory. Again, quick meme, when you fail to build your linked list, this is what happens. Broken linked list, very sad. All right, so before I go into any topic, I always like to give some motivation about like why should you even bother learning about this? Like why is this important in terms of interview prep and like coding interviews? And so let's say you're trying to solve a problem where you're trying to delete an element towards the front of an array, right? And so you might think of an implementation like this, right? So you might have to find the element at the front of the array if you have to, or you're given the element, and you have to delete it, and then you have to shift all the other elements back once. And so you're actually, the runtime of this algorithm is actually going to be linear time, right? You're going to have to, on average, go through some, like if let's say n was the size of the array that you're trying to delete an element for, you're going to have to, your algorithm is going to have a runtime of O of n. And this is because like it's really annoying because you have to move every single element that you didn't delete that is in front of what you deleted back once. And so now, imagine you're a computer, right? And you represent your file system and your uh, free memory in your computer, in like your, I guess your hard drive or in your RAM as an array, right? And each of these blocks represent how much free memory you have. And let's say you have like 10 free memory, and you have like 30 bits of free memory, and you have 40 bits of free memory. Obviously, I'm making an abstract estimation here, but you guys get the idea, right? And so if you're a computer and you have to create files, which means you have to delete these free memories, or you delete files, which means you have to create and insert these free memories at the place where they're free. And imagine if your computer, you would have to do this maybe on the scale of hundreds of thousands or millions of times. And so it moves on from being like an annoying part of the implementation to downright like costing you in efficiency. And if you have to implement an algorithm that does this operation many times, like millions or tens of millions of times, then the interviewer is obviously going to deduct you on your algorithm efficiency. And so you'll learn later in Edgar's class in CS 111, that's operating systems, which is a really cool class. You'll learn all about dynamic memory allocation and operating systems in RAM. But computer systems and operating systems actually use linked lists as an implementation to represent free blocks of memory. And so this is why it's like important to learn about linked lists. So I haven't really explained like the specifics about the implementation, but I just wanted to give some motivation, right? That like not only is it important for technical interviews and coding interviews, but it's also super important for more like other CS topics like dynamic memory allocation and like operating systems, right? Okay, now let's go over a quick overview of linked lists and more details about the algorithm, specifically the big O. So what a linked list is a collection of items stored on a non-contiguous location. And because it's non-contiguous, it helps us solve the problem we had before of having to, when you wanted to delete or insert something at the front of an array, you had to move everything else out of the way or into the new position that they now occupy. So because it's non-contiguous, you can ignore that entirely. And all you have to do with a linked list when you have to delete or insert an element is simply point the next pointer to either your new node that you're inserting or past the node that you're deleting. And so in that case, because of that, items in a linked list need not to be stored in any particular order. And so as you can see below in this chart, insertion and deletion of elements for a linked list takes constant time, so O of 1, whereas for an array, it takes O of n, it takes linear time. Now, of course, with every data structure, there are trade-offs, right? There's never going to be one data structure where you're always going to use, and you're always going to have to determine which data structure fits the problem you want to solve. And so, for example, when you're trying to access an element in a linked list, and let's say you know the specific index of the element you're trying to access, you would still need to traverse the linked list, right? By looking at each node and each node's next element until you've looked at enough elements in order to access the element that you want to, the node that you want to access. Meanwhile, with an array, if you know the index, you can instantly access the value at that index. You don't have to worry about traversing an array. You instantly have access to that value. And so in that case, access with an array is O of 1, and access of a linked list is O of n. And now with searching, for both of them, to search, you have to traverse the array or linked list. So for both of them, the algorithm is O of n time linear time. Now, I like to emphasize that kind of this chart and these big O values for linked lists and arrays and their operations are like super important in terms of coding interviews, right? And this is because oftentimes, or maybe like 90% of the time, when you solve a linked list problem or when you solve any problem involving algorithms or data structures, you're going to be asked the runtime and the big O of the algorithms or data structures that you used. And so knowing how to implement these algorithms is just as important, equally as important as knowing the runtimes and knowing the trade-offs between them, right? So like, this is super important. Now, linked lists can be singly linked or doubly linked, and we'll talk more about that later, but like know that there's a couple different types of linked lists. Oh. Okay, so what does a linked list look like? And when I'm talking about what it looks like, I'm talking about what does it look like in code, in implementation. So if we take a look here, this is how C++ linked lists are implemented. So actually, the C++ standard library has a pre-implemented linked list class, which can be used via including the list standard library. Now, the thing is that I would say more commonly, you will be given a struct to represent a linked list such as this, right? And you'll be given the struct definition of a single node of the linked list. And like you'll be given only the head of the linked list when you perform or you're trying to solve a linked list problem. And more often than not, the actual list data structure in the C++ standard library is going to be not super useful because interviewers care more about your knowledge of linked list operations, many of which, such as reversing a linked list or deleting a node in a linked list, which we'll talk about later again, rather than just having them pre-implemented for you in some C++ standard library, right? Now, of course, there's other C++ standard libraries that are super useful, like vectors and sets, where like you care less about the specific operations on each of the separate elements in those collections. But for linked lists, like operations that you do on each node is super important. And so I think it's probably okay if you mostly ignore the C++ standard library for linked lists for this specific list standard library if you're only caring about coding interviews, and instead to focus on problems where you're given a struct or a definition for a specific node in a linked list. Okay, now I'm going to talk about a couple different types of linked lists. So linked lists can either be a singly linked list where each node has a single pointer that points to the next node in the linked list. And in this case, the last node is represented by the next pointer pointing to null. You can also have a doubly linked list where each node has two pointers. One points to the next value node in the linked list and one points to the previous value in the linked list. And usually here you have access to both a head and a tail. And doubly linked lists are usually used in problems where you care about both the front and the end of the linked list. There are also circular linked lists where the tail points to the head instead of null, as you can see in this diagram here. And so usually when you're given a circular linked list, you're not actually given like any head value, but you're just given one node in the linked list where like arbitrarily, right? Because there's no way to determine like where's an actual head. Okay, and this is like another meme, but people like say if you want to explain a linked list to someone who hasn't encountered them before, you just like ask them for the 10th letter of the ABC because you have to like recite them from like A, B, C, D. You recite the alphabet to find the 10th letter. Although this isn't quite how linked lists are implemented, right? Because you're not looking at each specific letter and the next, and each specific letter doesn't tell you the location of the next letter. It does kind of resemble linked lists, so it is still pretty funny. Okay, let's take a look at a couple of basic linked list operations. So for these, you're most likely not going to be asked to like implement them. But the first node of a linked list is typically called the head. And if the head points to a null pointer, or like if the head is a null pointer, then the list is empty and you'll be given an empty list. And oftentimes you have to consider what happens to the algorithm when you're given an empty list as an input, right? What if you're just given a null pointer? For the last node in the list, the next pointer will be null, like I explained before. And to traverse a list, all you have to do is keep following the next pointers of nodes until you reach a null pointer, right? Now, this is specifically for singly and doubly linked lists. This obviously doesn't work for circular linked lists, where you're going to have to do some special operations and some logic to figure out when you actually want to stop traversing the linked list. Okay, another meme. This is a bit of an old one, but it still checks out. All right. So now I want to go into a couple of tips and tricks because it looks like you guys are quite experienced with linked lists. So singly linked lists are the most common. Usually, I would say 80% of the problems are going to involve singly linked lists in terms of coding interviews. And in most problems, you're just given the head. So it's always important to think about how to get to the desired element or linked list state from the head. Now, this is the most important part. I always advocate for using a dummy node when solving problems to avoid null access. Just like even if you don't think a dummy node is necessary, and when I say dummy node, I mean creating a node yourself that points to the head, or sorry, I guess that points to the first node in your linked list, and then like pointing your head to the dummy node, or have your dummy node act as the head. Um, and like, even if you don't think you need a dummy node, like oftentimes like it's hard to think of a reason to use a dummy node, but I would say just like always use it when you can, because it always saves you from the headache later on in an interview where you like encounter like a null access issue, like a seg fault, or you're off by one and that causes like kind of like memory issues. So always use a dummy node. That's my personal experience. And like I've been burned a lot of times because I didn't do this. Obviously, you guys are like free to, do your interviews however you'd like, but this is what I would recommend. Okay, great. Now, before we move on to practice problems, which of course is the best way to build your skills and your algorithm data structure skills for these interviews, take a break. We're gonna come back in 5 minutes, but drink some water, get hydrated, and get ready to solve problems. I hope you get hydrated. Welcome back, everyone. We can quickly get started with our first practice problem, which is just how to delete a noded linked list. So let's say you're given this, interviewer gives you this question. So first thing you have to do is obviously you have to read the question. So given a singular linked list and a target value, delete the node containing the target value. If there are multiple occurrences of the target value, delete the first occurrence. Now, I guess you guys are more experienced with linked lists, so I'm going to retcon this and say, hey, instead, this will say, if there are multiple occurrences of the target value, then delete all occurrences of the target value. And then, of course, assume that nodes have this following struct definition. And so take like 2 minutes to read it or 1 minute to read it, and we'll go over and hop over to Replit so we can get started. Now, of course, in the spirit of following kind of the steps that we outlined in the first session of like how to approach a problem during a coding interview, is obviously the first thing to do is to like read the problem and maybe like repeat it back to everyone and to your interviewer, so that you make sure you understand the problem in the same context that the interviewer presented it as. And the second thing to do would be to come up with possible questions that you have about the problem. Definitely ask about the edge cases that you've thought of, the input and output parameters, like what you think, like could cause an issue for the implementation. So for example, a great question for this, if let's say they don't tell you that if there are multiple occurrences of the target value, you should delete all occurrences. You should ask that, like, hey, what happens if there are different occurrences of the same value? You can also like clarify like, okay, is the value specifically an integer? Because this problem doesn't tell you, only like this definition tells you. You're like, hey, should I be using an integer? As well as like, hey, is this if for example, they don't tell you it's a singular linked list and they just said given a linked list, you could ask like, is this a singular linked list? Is this a doubly linked list? Etc. You can also ask like, what should I do if I'm given a empty linked list? So just like a null pointer. Should I throw an error or should I just like return the null pointer without having done anything to it? And like what happens when the only occurrence in the linked list is the target value? So should I just return a null pointer in that case? I can see someone typing in the chat, I think. Oh, no, never mind. Yeah, and so let's now hop over to the replit. Can you guys still see my screen? Okay, great. And can you guys see the replit now? Okay, nice. Let's get this now. Okay, cool. So now we have our definition of the struct. And so I'm going to quickly write out the function definition. So what we want is we want to delete. Let's say we want to return this node occurrence. And let's say you're just given only the head. Okay, cool. And so now that you have read the question and that you've asked clarifying questions, now is the time where you're trying to like brainstorm a possible solution, right? And so I'm gonna give you guys 15 seconds. And if you have any ideas of a possible implementation or solution, go ahead and either unmute yourself or type in the chat. Oh yes, great catch, Matthew. The function should accept the parameter of the value. Let's say val to delete. Anyone got ideas? Okay, I'm going to guess that because no one is typing, I'm assuming that everyone like already knows how to do this or knows how to implement this. It's like super good at it. So I'll go over the solution for this problem really quickly. So just to go over like one test case first, let's say you're given a linked list where it goes from 1 to 3 to 1 to 4 to 1 to 6, and the target is 1, and you want to delete all occurrences. So let's make this delete all occurrences. You would simply return a list node where the head points at 3 and the linked list is 3 to 4 to 6. Okay, cool. And so the first thing you would do probably when approaching this problem is, so you would read the question, then you would ask clarifying questions, and then you would brainstorm for a solution, right? And you would like first, before writing any code, you would think, okay, how do I approach this? And like, what is a possible implementation for the solution? And most likely you would do this out loud so the interviewer can like understand your thoughts. And so the first thing that comes to mind here is like, okay, I can simply traverse the list using 2 pointers, one pointing at the previous value that I just visited and one pointing at the current node. And every time I encounter an occurrence, all I have to do is move the next pointer of the previous node to the next pointer of the current node, and then delete the current node, and then move the current node to the next pointer of the current node, right? And you would simply do this in a while loop, and eventually you would end up deleting all of the occurrences, right? So yeah, I guess we can get started with the implementation then in that case. So here, if the head is a null pointer, empty, looks like rep is lagging a bit. Hold on. Okay, here we go. Hopefully you guys can see my changes. Okay, great. right? Okay, and now I'm gonna again follow the advice that I just gave out earlier. Create a dummy node, which I'm just going to initialize to new this node and to 0. I don't really care what it is. And the dummy node is going to point to the head that we give it. And at the end, we want to make sure we delete the dummy node so we don't cause a memory leak. So what we can do is we can get the return value that we want, which is going to be the dummy next. And dummy next is always going to be the return value. So even if it's like a null pointer, that means we just deleted all occurrences of all nodes in the list. And we can, at the end, return ret, but not before deleting dummy. Okay, great. And so now we want to keep track of the 2 pointers I mentioned before. So we have previous, which is going to point to dummy for now, and current pointer, which is going to point to head. And we can make a for loop. So while the current pointer is not null pointer, so while we haven't reached the end of the linked list, okay. So while we haven't reached the end of the list, what we can do is we can check to see if the current node's value is equal to the target. So we can check the value is equal to 8. Right, and if it is, we can do the deletion operation. So we can set the next to current next. And here we want to delete the current, but we got to be careful. First, we want to set a temporary list node pointer that points to current, and then we can set current to current next to move the current pointer to the next pointer. And then finally, we can delete the temporary pointer. Great. And of course, if we don't encounter the target value, in that case, we can simply iterate the previous pointer to the next previous next pointer, and we can do the same thing with the current pointer. Okay, and that should pretty much be it in terms of the implementation of the algorithm. So first, I want to make sure this compiles. I am getting a couple of errors here in terms of this. Make sure this compiles. Okay, cool. So it looks like it compiles. Yep, it compiles. And so next, what you would do is after implementing your solution is that you would write some test cases. So oftentimes you're not going to be given any test case, or you're going to be given test cases, but they're going to be in like plain text. And so the interviewer is going to say, hey, now that you've implemented your solution, please write some test cases to verify your solution. Even though like they might have test cases already prepared, but they're going to do that later, and you have to write your own test cases to show that you can write unit tests, because those are really, really common in industry. And writing test cases for your like isolated algorithm is just like writing unit tests. So here, what we can do is we can like create a bunch of list nodes. Bunch of values. Let's say we want to use the test case that we used here. So we just create them here, and I'll just copy paste them. And I think it's actually really important to, like, when you solve these problems, also practice making test cases for them, because you don't want to be able to, like, really quickly solve a problem and then be like, okay, yeah, I don't know how to make, an example test case for this like tree problem or this linked list problem, because like that'd be really awkward, right? So here we're going to set it up. And we, of course, have to set the next pointers up. So that's 1, next pointer, that's 2, do the same. Oops. Times, okay. And afterwards, you're also going to have to write a way to print out your solution in order to verify the dot. So let's take this, delete all occurrences, and let's enter the head node that we're given. So test1, and then here, we say while this pointer isn't null pointer, you can print out the value, and we can iterate this. Okay, let's see, make sure this compiles. Let's see. Oh yes, I need to give a target, so we want to do 1. So, okay, great. So it gives us 3, 4, and 6, which is the correct linked list we should have gotten after deleting all the ones in this list. And for example, we can try deleting 3s, and it should just delete the 3 and give us 1, 1, 4, 1, 6. So we run it, and it does give us the correct solution. And so congrats, you just walked through what you should do if your reviewer gives you a linked list problem, and you know now how to solve a specific linked list problem, which is to delete all occurrences of a value in a linked list. And we'll go off and take a look at the next problem, which I believe Sartak will go over.
But before that, we're going to ask you to poll if you like
Yes.
that explanation.
You're going to get polled to see how you found that problem and how you found its explanation for that problem. Great, great. Thanks for voting. And we'll move on to the next problem. Oh, before then, here's a quick meme. Okay, great. You have the floor, Sartak.
Okay, so hi everyone. Our next problem is merge two sorted lists. So in this problem, we're given two linked lists, and you can assume that you were given the head pointer of both lists, and we want to return a new linked list, which merges the two lists. So the merged list should be in sorted order also, and then we just want to return that list. So for this problem, we'll give you some time to think about it on your own. So we'll put you in breakout rooms for about 5 minutes. If you guys have any questions during that time, message the chat. If you need more time, message the chat. But yeah, after that, we'll come back and talk about it.
Okay, so I will stop sharing. Oh, looks like you've already split them. Okay, great. Okay, do one of you, like Sartak and Anna, do one of you guys want to join each of the rooms?
Yeah, sure.
Yes. I had to move him. I was like, why aren't you going? So I moved him to room 1 and I moved him back to room 2. Okay. So you guys can move around freely, right?
Yeah, I think
I'll
so.
go to 2.
Okay. I mean, you can go back. Okay.
Hello.
Okay.
What?
I'll pause the recording. Sorry. Okay, so welcome back, everyone. I saw that in my breakout room, at least, everyone had like a pretty good idea of how to solve the problem. I think Anna can say the same. I like popped in for a minute. But okay, so let's try to write the code for this problem. So first, I'll just write like a function where we can solve the problem, and we'll call it merge two lists. Okay, yeah. So the first thing we want to do is restate the problem, even though we've done that multiple times. But basically, we have two sorted lists, and we want to create a new linked list, which is also sorted. So just to go through like a test case first, we'll go through like the test case that was in the slides. So I think it was, the first one was head 1, 3, 4. And the second list was 2, 5, 7. And so as a sorted list, I think the first one would be 1, 2, and 3, 4, 5, 7. Okay, so like we have, so let's say like we just have a bunch of numbers, and we want to create like a sorted list from that set of numbers. So we can do that by repeatedly picking the minimum element from the set. So like, let's say we have like a bunch of numbers, we pick the minimum one, put it at the front of our array, and then we pick the next minimum, put it at the front of our array. And I think in general, that's called like selection sort. And out of the sorting algorithms, it's usually a bad choice. But in this case, since the two lists that are given to us are in sorted order, we know that the minimum element from those two lists must be one of the first elements. That's because, you know, the minimum is at the front of the sorted list, and since we have two options, we picked the minimum of those two elements to find the min in the whole set. And then what we can do is pick the min out of the first two, add it to our list, and then pick the min out of the remaining first two. So like we would like shorten our list, the one that we picked from, and then find the min between the two heads and add it to our list and continue doing that. So when we do this, we have like two options. So when we add the node from the two lists to our final list, we have the option of either creating a new node, or we can reuse the nodes in the linked list. And I think here we can assume that we're allowed to change the original list. So I think it would be better to use the lists in the original list, use the nodes in the original list, because then we'd be saving on space. Okay, so let's try implementing this. So first, I think this would be a good example of where to use a dummy node, like Bo was talking about. So we'll make a dummy node. And the purpose of this dummy node is just to point to the head of our linked list. And later we'll see like how this saves us. And then also I'll define a list node pointer called cur. And for now I'll set it equal to dummy. And the purpose of cur is to point to the end of our linked list that we're going to return. And so now we can start finding the min and adding it to our list. So here, I'll first consider the case where both lists have elements remaining. So that means that L1 must not be null, and L2 must not be null. So in this case, we check the first element and compare them. So I'll first compare L1 to be less than L2's value. And so if L1's first value is less than L2's value, then you want to add L1's first node to cur. So we'll say cur's next is L1. And then we want to advance L1 because we want to shorten the list that we picked from. So I'll say L1 is equal to L1's next. And we also want to advance the list that we're creating. So we'll move cur to cur's next. And this is safe because we've already set cur next. In the else case, this is when L2's val is less than or equal to L1's val. So it's the minimum. And here we'll do like a similar thing. So we set cur's next to L2. Then L2, we shorten L2. L2's is equal to L2's next. And then cur next. Okay, so until both lists have elements, I believe this would work correctly. So next, we will have reached the end of one list. And at this point, we only have like one list to pick from, and we know that it's sorted. So all we need to do is add that sorted list to the end of the list that we're creating. So what we can do is check to see which one is still remaining. So first I'll check if L1 is not equal to null. That means we add L1 to our list. So I'll say cur next is L1. And then we also check if L2 is not null. I could have just been else, but to be fancy, to be clear. And so now I believe we have correctly merged them, ideally. And now we just want to return the head of our linked list, and that will be pointed to by our dummies next. So I'll return dummy next. And also, just to avoid memory leaks, we can store this and delete the dummy and return this. Okay, so first I'm going to compile. All right, okay. I'm just going to comment this out. Okay, so it looks like it compiles, so I didn't make any major issues. So let's try testing it like you would have to do in an actual interview.
I have a quick question.
Oh, there's a question in the chat.
So at the end of like in your while loop, you wrote cur gets cur next. Like you wrote that twice. In interviews, is it cool? Like if would they consider it like quote better if you wrote it at like the end of the while loop, or does it just not matter?
Oh, I think, yeah, maybe it'll be nicer because you recognized that it's in both cases, but I don't think it would make a big difference. But yeah, I think it's one line less, so yeah, shorter.
But like there's no like better option. Like you won't get like points knocked off or anything, right?
No, I don't think so.
All right. Cool.
Yeah, unless it's like you're doing like a bunch of code and you're copy pasting it. Okay, so test case. So I'll try to do the same test case as we wrote up here. So 1, 3, 4, and then 2, 5, 7. And then that's our first linked list. This is our second. And then I believe that should work. So I'll uncomment this, call our function. On L1, sorry, test1, and test4, and then we'll print out the linked list. Okay, let's see. Okay, yeah, so we were able to correctly merge the list. Now, in an actual interview, it'd be better to go through some edge cases as well, but I'm just going to cheat and say that it works. But yeah, now you guys know how to merge two sorted linked lists.
Okay, great. Thank you, Sarthak. We're going to poll this question as well, just to get a gauge on how you felt about, oh, I think this is the wrong question. But we're going to try to poll about how you felt about the question and how you felt about the explanation, just the difficulty. And I think Anna is going to explain the next question.
Yes, hello everyone. Looks like everybody really liked that last question. It felt like a pretty good difficulty for everybody. So let's, I guess I would say this is slightly harder, rotating a list. So if you don't know what, I guess it says it right here, but basically we're going to be given a singly linked list, and then we're going to have to rotate it to the right k times. As you can see from the example inputs, so we have 1, 2, 3, and then that's then. So our list is 1, 2, 3, and then we're going to rotate it k 2 times. So then it's going to be 2, 3, 1. Does everybody understand? That's good. And then also, as you can see from the second example input, k doesn't actually have to be less than or equal to the length of the list. So k equals to 8, and you can just loop it 8 times. I guess not loop it, but change the position 8 times. Okay, so let's go right to Replit. Actually, yeah, so I'll copy and paste the question statement as well, just so that it's easy to read. Yes. So what should we think about first, right? Like, as I said before, k doesn't actually have to be, you know, less than or equal to the length of list. So what should we do in that case? Like how do we even know how long a linked list is, right? Like we don't, like usually with a singly linked list node, the only data field that we actually keep track of is the value that it holds as well as the next. So does anyone know how we can get the length of the linked list? And just type it in chat, or you can shout it at me. Either way. Correct. So Lens are completely correct that we have to actually traverse it once entirely first in order to know the length of the list, which is fine. I think is essential for us to know how long the list is. Okay. So anything else we have to watch out for? Can anybody like throw something out there that they think could trip us up for an edge case? Negative k, right? So definitely, like if it's negative, do we, rotate to the left? Do we leave it alone? Do we just exit? What should we do? So in this case, ask your interviewer, and I as an interviewer would just be like, okay, well, good thing you noticed. If you get less than 0, then just return null, or you can return the original list. It doesn't matter to me, but thank you for clarifying it with me. Okay, I guess the one that's very easy is what if k equals 0. If k equals 0, then we actually don't have to do anything, so we can just return the original head, right? So I think we covered the most basic things that we should be thinking about for this particular question. And so I think we should get started. Okay, let's see. Actually, Replit is being very slow. Okay, so function name, let's call this, we're going to be returning a list node pointer, right? So it's going to be list node pointer star rotate right. We're going to be passing in our head node as well as our k in order to rotate it 8 times. Okay, so let's go over this. So we went over k equals equal to 0, right? K equals equal to 0, then we should just return the original node. Okay. Oh, wait, I didn't put the region there. Okay. Okay, this brings up another question. Oh, when I was coding this up, what if we didn't even have a node? So like when we pass it in, we call this, and there was no head node in the first place. What should we do then? Right? It should be fine. As long as we check for that. So, obviously, if explanation point not node, so this will just check if it's a null pointer, then we can return node, or we can return null pointer. It should not matter regardless. So that sounds good to me. So when I think about this question, I think when I originally saw this question, I thought of Bill going over a circular list. I was like, okay, well, if it's a circle, then I can traverse it as many times as I want without having to worry about, the end of the list or like the length of the list, right? Because even if k is greater than like the length of the list, if we make it circular, then it would just go however many times it needs to, and then we can make the new head, whichever the one that we land on, right? So that was my thought process, but obviously when you see this question in the future, hopefully you can think of it a different way. So like obviously like what Lorenzo was saying, keep track of the length of the list, and because a full circle, when you make like if your length was 3 and your k was equal to 3, then technically you didn't actually rotate because you just came back to the original start. So can anybody tell me how that operation could be represented in like just like a 1-line statement, how we could find what the new head should be? Obviously you don't have to know, but it's just
use the mod operator.
Exactly. Good job, Aiden. Use the mod operator. So if k, so we can do something like k equals to k mod. It's not mod. Right. And what's the mod operator? Percent sign. I would like to make. No. Oh, but wait, we don't actually know the length of the entire list, right? So we actually have to find that out. So obviously this is more like pseudocode. It's just something we should keep track of. So obviously next thing we should find out is the length of the, what's it called? The length of the list, right? So we can, initialize our name because we know for sure there's at least one node after checking the first if statement, if there is a node in the first place. So we can initialize our length to 1. And then we're going to be keeping track of our original list, the head of our original list, just because after we traverse it, we wouldn't be able to, come back to it after we find it. So let's call this OG head, and then, while node.next is not null, because we don't want, this just means that, if when we break out of it, this will be the last element that we see, the last node that we will be seeing. Obviously, if you have any questions, feel free to, not call me out, but just basically, let me know. Because I can't see the chat, unfortunately. So like any standard operation, we're going to do node equals node next. It's pretty standard for traversing the linked list. I think all you guys know, as well as link plus equal to 1. Okay, looks good to me. So now we can say, okay, well, as what Aiden said, our new K is equal to K on length, right? Because that's going to be, as long as we're traversing more than the length of the list, and technically we're just going to be moving. Okay, so obviously my thought of this question, I wanted it to be a circular linked list. So in this case, I would do, I would do a for loop, and then I would just be like, okay, well, how many times do I have to move right? So I would just move however many times K is, right? And then make my new head that. Does that sound good? Okay. I actually don't know if it sounds good because I can't see the chat. Okay. We're going to make a new head because we should keep track of that, right? So this node star, new head equals our original head. And remember, no, we can't make this node because nodes actually are the last, like the tail of our original list, right? Because we can't access the head anymore after we traversed it. So don't make the rookie mistake of setting it equal to node, or just like not having a backup of like keeping track of the original head. That's something to keep track of. Okay, so now we do new head equals head. Don't know why. Okay, showed up. Sounds good. And so, great. Does this look like good code to you guys?
You should return the old head or the OG head.
Excuse me?
Oh wait, never mind. My bad.
It's okay. I like what's it called?
I think you need to change manually, change from the regular linked list to the circular linked list after the while loop, right? Because it's pointing to no. So you have to
yes.
Yeah.
Right. So I didn't actually turn it into a circular linked list. So that's a good catch. So I didn't actually turn it into a linked list. I'm going to now turn it into a circular list. Let's do so node.next, right? That's actually our tail right now. So now we're going to let it equal to the original head. But this brings up a question. So you should ask your interviewer this when you when you talk to them. You're like, okay, well, I made this into a circular linked list, but do you want me to return the original, like make it into a singly linked list? And obviously, I think the answer would be yes, like return it back to me how it originally was, right? If I give you a singly linked list, then I expect a singly linked list back. So in this case, we're going to be giving back a circular linked list, and that's not good, right? So in this case, we actually have to be setting the tail as well every time after we made it into a circular linked list. Does this sound good? Okay, I can't see the chat, but I think it's good. So in this case, our new tail, right? That's going to be after we every time we set the new tail is going to be, we're going to let it point to, currently it's going to be the node right now, because after we traverse the entire thing, node is the last element, which is the tail. We're just going to set new tail initiated to our original tail, just so when we traverse it, then we understand. And then in our for loop, that means that we're going to be also moving the new tail one at a time. So new tail equals new tail next. And then new head is also going to be new head next. So basically it's kind of like 2 pointers. One's going to move forward and one's going to move backwards. So they're always going to, the length between new head and new tail is always going to be the length of the list, right? Because that's what we set it as originally. Does that make sense? Okay, so after this just means that we have, you know, we still have a circular linked list, but we know actually where the tail is and where the head is. So after we know where the tail is, then we should set the next of the tail to be null. So that would cut off the, you know, the circular part, and then we would be left with a single linked list. And afterwards, we return new head. And does this look good to everybody, or do you think I did something wrong? Hold on a second. Okay, obviously the most important part, you know, you can say your solution all you want, but the best part, I guess, to demonstrate your ability is to test your code. So I'm just going to probably be using our, you know, original sample input and output. So instead of 1, 3, 4, let's just call it 1, 2, 3. I think I would like it to. Okay, so 1, 2, 3. Then test 1 next is test 2, and then test 2 is next is test 3. That's good. No, we don't need this item. So we're going to, this is not called merge two lists, this is called rotate right. I would like to rotate. We're going to be calling it on test 1. And then as well as, what's the original K? I think it was 2. Yes, it was 2. We're going to call that. And obviously, like Bill said, be sure to have, you know, a nice way of like writing out, testing your input and like seeing how it looks. So our while loop basically here is doing the cout statement. So let's test it and see if it works. Oh, okay. So it actually is not 312. It's 312 instead of 231. So what can we find differently here? I think it's our mod statement, because our K is 2, 2 mod 3. Actually, 2 mod 3 is still 2, right? I'm actually not sure. Is 2 mod 3 2?
I think so.
2 mod 3 is 2.
Yeah.
Let's see, let's see. So this becomes 312 instead of 231. So in that case, that means that we rotated. So it's 1, 2, 3. And we rotated.
I think it would be rotating to the left instead of to the right.
I see, I see. Okay. So instead of that, so we should make this for loop instead of rotate. So instead of the new head next. Okay. Fortunately, I don't think we have enough time, but.
Or can we change the, like the second loop, we change it to something like the, I'm not sure, length, like the length minus K. Can we do that? Like if we want to do it the other way? It's just, yeah, I'm not sure at all.
If we do length minus K, then it's possible that, oh yeah, actually, you know what? We can try that instead of, so it'd be K equals K mod length, but then we would do K equals length minus K again. Oh wait, this actually, I think just turns it back.
K, yeah.
Length minus K, sorry. Okay, so our crappy patch job works for now, and let's go through this. I think instead of, so we would just be rotating extra, I think, in this case. Sounds good. Anybody have any questions? I probably will be annotating this a lot more during our solution write-up. So if you have any more questions, you can refer to that when we post it. But
Yep.
is there anything else for now?
We'll be polling you guys as well to see how you found the difficulty of this question and clarity of the explanation. That poll should be up pretty soon.
Should I do it?
Yeah.
Okay.
That's nice. Okay, great. Looks like a lot of you found this problem just right. It's definitely harder than last two problems, but I think it was a good progression between easier problems at the start and then harder problems as we go on. Okay, great. Now we'll get back to our last slide, which is just showing off our link to the response form for any feedback you guys have. Since we take feedback really seriously because not a lot of people fill out this form. So if you fill out the form and you have any suggestions, we're gonna actually consider your suggestions seriously. So please fill out this form and we will take a look at it afterwards. Otherwise, that's the end of the session, and join us next week for our next lesson.